we're still on 9b. Going to do some kind of overlap, different ways to look at it. We're going to look at probability tests that you can use to test if two events are mutually exclusive or if two events are independent, right? And we're going to use conditional probabilities in these tests. So just to remind you, this is one way of phrasing it. Two events are mutually exclusive if they have no common terms, right? So an example of that would be A is getting a heart and B is getting a club, right? They are mutually exclusive. You can test that by finding a conditional probability. If the probability of getting A, given that B has hand, if that is 0, then the two terms are mutually exclusive. If this probability is any number, then they are not mutually exclusive. So if you had two events and you were trying to figure out are they mutually exclusive, you could do this test. Find the probability of A given B. If the answer is 0, they're mutually exclusive. If it's something else, they're not. Two events are independent, and sometimes people confuse mutually exclusive and independent. But two events are independent if the probability of the first thing happening has no effect on the probability of the second thing happening. And the test for this is the same guy. If the probability of A given B is the same number as just the probability of A, then these two events are independent of each other. If this answer is not the same number as the probability of A, then these two events are independent. Okay, so let me pick an example of this and then do a different kind of situation for that one. Let's suppose we do A is clubs and B is red cards. I think by inspection, would you be able to say they are definitely mutually exclusive, right? Pretty obvious. A club can't be a red card and a red card can't be a club, right? They share nothing in common. But if I was doing it as one of these, we would say, what's the probability of getting a club given that it was a red card? Well, since you know it's a red card, does it not make the bottom number 26? Right, because there's 26 red cards. How many of those 26 red cards are a club? None. So don't you get exactly what you were expecting? 0. Let's do A is clubs and let B be a king. Would you agree that they are not mutually exclusive? Isn't there a king of clubs? Right? So if I did what's the probability that you get a club given that it was a king? Well, since you're told it's a king, does it not make 4 cards on the bottom, right? 4 kings. And how many of those 4 kings are clubs? 1. Do you see that the number isn't 0? Conclusion, well, in this one here, the conclusion is A and B are mutually exclusive. And the conclusion here is that A and B are not mutually exclusive. Most people could figure that out just by looking at the stories, right? Couldn't you look at them and say nothing in common, mutually exclusive? Wait a minute, there's a king of clubs. Not mutually exclusive. But what we've got is a test. Now, how can that be useful? Well, if I tell you I've got 2 events, A and B, and I tell you the probability of A given B is a third, can't you tell me right away that they are not mutually exclusive? Even although you don't know what A and B is, all you're being told is a conditional probability using A given B. Now, those are pretty easy to do basically from knowledge. Independence sometimes can catch you. So just to remind you, 2 events are independent, right? if the probability of one has no effect on the other one happening. So our test is a conditional probability, the same one, and it should equal this. So let me give you an example of events that are independent, even although they don't seem to be. Let A be a king and B a red card. Now, if you went and said, are those two probabilities, right? The probability of getting a king and the probability of getting a red card, are those two events independent? Well, you might falsely think, well, they're from the same deck of cards. One's going to affect the other. Let's find out if they do. The probability that you get a king, which is essentially what the probability of A is, would you agree that that is 4 out of 13? Great. Now, let's find the probability of A given that you were a red card. Right? Since you know it's a red card, does it not make it 26? And I guess I shouldn't have called that A, shouldn't have called that king, right? Would you agree that's 26? How many of those 26 red cards are kings?
Two.
2 or 4? Which is it?
2.
Would you agree that the probability of getting a king, given that says red card, is not the same thing as the probability? Oh, wait a minute. It is the same. Isn't it 4 out of 52 for a king? Ah, it is the same as a king. Right? 4 out of 52 is 1/13. What that means then that these two events do not affect each other as probabilities. So getting a king and getting a red card do not influence each other. If I got a king, the chances it's a red card is just going to be the same, whether I knew it was a king or not. Pick a different one. Suppose A is getting a face card. And let B be getting a king. Right? Right, the probability that you get a face card, right? This time I make sure I get the bottom number right. How many face cards are there? Well, there's 3 in each of the suits, so that's 12 out of 52. You get 3/13. Let's find the probability then of A, which is a face card, given that you knew it was a king. Well, since you know it's a king, doesn't the bottom number get you 4? You okay? Right? How many of those?
12.
Robert?
How does 12 of 52 equal 3 of 13?
I hope you divide the top and bottom by 4 and it simplifies down.
Never mind. I see it. Yeah.
Right. Okay. So what's the probability of getting a face card given a king? Well, we know there's 4 kings. How many of those kings are face cards? All of them. Would you agree that these two are not equal? Right? If they're equal, A and B are independent. If they're not equal, which these clearly are not, right? They're not equal, then A and B are not independent. That kind of makes sense. If you know it's a face card, wouldn't that alter your chances of getting a king? Right? Or if you know it's a king, it alters the chance that it's a face card, right? We know that those two interact. Kings and red cards don't interact in any meaningful way, because knowing something's a king doesn't improve your chances that it's a red card. Knowing that it's a red card, doesn't it not change your chances that it could be a king, right? Those two things are not affecting each other. Would you also agree that these two things are not mutually exclusive? Aren't there some kings that are red cards? Aren't there a lot of kings that are face cards? So can you see that these two ideas are not the same? You could be independent and mutually exclusive, right? You could be both at the same time, but you could be independent or not independent and exclusive as well, right? That could happen. Are we good with that so far? Right. So let's pretend I gave you a question like this. The probability of A is 1/5. And the probability of A given B is 3/7. And the probability of B is 4/9, right? And that's all I tell you. Okay. Now, from that piece of information, here are some things that you should be able to tell me. Are A and B mutually exclusive? And you should be able to tell me, are A and B independent or not? Okay, let's go for mutually exclusive. The probability of A given B is a fraction, in this case 3/7. Does that make A and B mutually exclusive or not mutually exclusive?
Not.
And the reason is that it ain't 0, right? So we would choose not mutually exclusive. Okay. Are A and B independent or not? Correct. You're shaking your head, Lauren. Tell me why. You're right. They're not independent.
Because they don't equal each other.
And shouldn't they equal that guy if they're independent? But, hey, so they're not independent. See, that little test is quite useful when you don't know a lot about the story, but you do know about the probabilities. Okay. So let's expand that idea to a table. Let's suppose I collected the sample. And this sample asked men and women who they were going to vote for in the next election. And they had, just to make my life easy, they either said conservative or liberal, right? Or what would that be? Republican and Democrat. So they said Democrat or they said Republican, right? And in the men, it was 70 and I'll just make nice numbers, 130. And on the women, it was 70 and 30. Now, from a table like this, we can calculate lots of different probabilities. And to make your calculations easier, it's very often that you put the totals of rows and you put the totals of the columns. And then you have a grand total. Like, I've done that all, but that should be adding up to 300. Ah, that's better. There we go. Now, show you how this would work. If I randomly choose one of these 300 people, the probability that it is a woman would be 100 out of 300. You'd be comfortable with that being a third. Now, what about if I found the probability that it was a woman, given that she voted Democrat? And you might say, well, how can you do conditional probabilities? You do it this way. If I tell you that it's a Democrat, doesn't the data just become that top row now? And so how many of that 140 were Democrat voters? And the answer was 70. And so that is a half. Agreed? Now, the probability that you're a woman, given that you're a Democrat, if I compare that to the probability that you're a woman, isn't that basically A given B and comparing it to A? Would you agree that 1/3 is not equal to a half? Agreed? The probability that you're a woman given you're a Democrat is not the same answer as just being the probability that you choose a woman. What does that tell me about women and Democrat voters? Are they independent events or not? This is not equal to that. Does that make them independent or not independent?
Not independent.
So we can say that women in voting Democratic, right, are not independent. Well, in English, do you know that essentially means that women vote differently depending on the party? In this case, let's take both situations for the women. I've already found the probability that you chose a woman given that they vote Democrat, right? And the answer for that ended up being 1/3. What's the probability that you pick a woman given that she voted Republican? Well, wouldn't the world now turn into that bottom row, right? If you're told they're a Republican voter, it goes this way. So what does that look like? Well, 160 out of 30, that is 3/16. From these two, wouldn't it be reasonable to say that women vote more Democrat than they vote Republican? If you want to see it as a decimal, that's about 33%, very roughly, and 3/16 is about 19%. Now, does that help see the difference between the two? That's what you found out. When things are not independent, right? It means being a woman and voting Democrat are connected in some way. In other words, women either vote more than they should or less than they should, compared to the average. Do with the men then. What's the probability that you choose a man, right? Well, if you look at how many men there were, there's 200 out of a total of 300. So if I choose somebody at random, right, with no other restrictions, the chances that I pick a guy is 2/3, right? 200 out of 300. Now, what's the probability that I choose a man, given that, let's say, he's a Republican, right? So we know it's a Republican. What's the chances that it was a man that I got? Well, since you know it's Republican, right, it goes here. And wouldn't the men be 130 out of 160? And let's call that 0.67 to make it easy to compare. If I take 130 and I divide it by 160, I get 0.67. 1 roughly. Do you see they're not equal? Does it not make those two things dependent as well? In fact, doesn't it look like men vote Republican more than women do? And I kind of twisted the numbers just to get the idea, but that's actually true. If you look at the voting patterns, women tend to vote more Democrat than Republican, and men tend to vote more Republican than Democrat. For whatever reason, that's a pattern that at least has happened over the last few elections. There are always going to be changes, right? But what we're able to do now is we can analyze this table using conditional probabilities and find out whether things are connected or not. Do another one of these, show you how it might work. Let's suppose we did a very, very simple table. And we're going to have alive and dead. And we're going to have people who smoke and people who don't smoke. And so you did one of those observational situations where you followed, let's say, 1,000 people. And after 10 years, you found out how many were alive and dead, and you found out whether they smoked or not. So it'd have to be observational because you can't make people do that. And we found out that, try to figure out how to do this table. Red will do. Right, so the smokers, 200 are dead and 200 are still alive. And for the non-smokers, we'll do green. And for the non-smokers, it was 500 are alive and 100 are dead. And if I did this right, which I hope I have, 700, 300, 600, 400. We agree? Now, I've deliberately tried to make the data come up with the result I wanted. What I'm going to look for here is there any connection between people who smoke and being dead at the end of 10 years? Because if those things are independent, wouldn't smoking have no effect on your livelihood, right? You're just as likely to live as long as anyone else. Smoking doesn't really have any effect, right? That's what independence would mean, right? Smoking and being alive at the end of 10 years or dead, doesn't matter. So let's find out what's the probability that at the end of 10 years, they were dead. And 300 people had died out of 1,000, and I'm going to keep them as decimals. 0.3, 30% of them are dead in this particular story. Now I'm going to find the probability that you were dead given that you were a smoker. Now, since you are told that you're a smoker, do you see how you make the top row your data? And there are 400 people in that group, and aren't 200 of them smokers? Right, 200 of them dead, I should say, out of these smokers. And that comes out as 0.5. They're not the same. Does it not make these two things, that's being dead and smoking, are not independent? I actually prefer the word dependent. Not independent doesn't get the idea. Dependent, right? One depends on the other. One is affecting the other. Would you agree, at least based on this data, that smoking has an effect on your chances of being dead? In fact, in the way this data works, aren't you more likely to be dead if you're a smoker than if you're not a smoker? So can you see how you can use little tables like this to decide if this thing and this thing are connected or whether they don't affect each other? Because if you just looked at the raw numbers, wouldn't it be quite hard to tell? Because, you know, there's a different grouping of how many smoke against how many don't, and there's different amounts have died, and, you know, how do you interact? It's hard to do. I don't have the time, but can we pretend I did another table and we found out that the probability that you eat ice cream was 9/10 was 0.9, and the probability that you were ice cream and that you were dead at the end of 10 years ended up being 0.9. In that case, wouldn't eating ice cream and being dead have no effect? They're independent events. They're a horrible thing. You think 90% of your sample died on you, but whatever they died of, it wasn't eating ice cream that caused it, right? Because this probability and this one are the same means that they are independent of each other. They don't affect each other. And that's how we test it. Any questions? Are we good? Right, let's look at some examples of tables, and then after that we can look at probability questions as well. So with a bit of luck, I'll get this section finished today. Right, we're on question 14. When 192 students were asked to pick a digit from 1 to 10 or a number from 1 to 10, the number of students selecting each number were given in this table. Okay. What is the approximate probability that someone asked to pick a number from 1 to 10 will pick a 5? I don't think you need salt for this. Wouldn't it be 18 out of 192? And make it a decimal to 4 decimal places. So you would just go 18 divided by 192 and then figure out 0. What, you know, whatever it is. Now, what is the approximate probability that someone asked to pick a number from 1 to 10 will pick one of the two extremes? So the two extremes would be this side and that side. So wouldn't that be what, 8 out of 192? You comfortable about that one? And the last one was odd numbers. Well, if you wanted to do what's the chance that they picked an odd number, wouldn't you just add up all these guys here? Aren't we allowed to do all of those calculations because each of these things are mutually exclusive? And when they're mutually exclusive, you just add them up. Right, 15. 182 students, yeah, that matches that, were asked to pick a number from 1 to 10. The number of students selecting, oh, I've seen that question before. Suppose that a student is asked to choose a number from 1 to 10. Define A to be the student chooses the number 4, and B, that they choose an odd number. Okay, so A is you choose a 4, B is you choose an odd number. What is the probability then that you choose a 4 and an odd number? In other words, both at the same time. Would you agree that that ain't going to happen? You can't be a 4 and an odd number. Remember, this is the and word, not the or word. That would be different. Then, because of that, are these events independent? And explain how you know. They are not independent. One does affect the other, doesn't it? If you pick a 4, it doesn't have an effect on whether it's going to be odd or not. Now, are these events mutually exclusive? They are, and off you go and do that one. Okay. This one is to do with English. In a given year, so we don't have calculations really to worry about. In a given year, in a particular country, there were about 62 births per 1,000 women aged 20 to 24, and about 96 and a bit births if they're aged 30 to 34. Based on these numbers, are a woman's age and whether or not she gives birth is a given year is likely to be independent? Well, I don't think the numbers actually matter. I think they're a red herring. Do you think the chances that you give birth is dependent on the age of the woman or the age group of the women that you're looking at? I would say yes. Let's be silly. Do you think the percentage of women in the age group 20 to 30 to have babies is different from the age group 40 to 50? I would expect a lot more women to have babies in the 20 to 30 than the 40 to 50. So what I'm saying is that the age of the mother does affect the probability. And if one affects the other, right, age and how many children you have, you're looking at a dependent event, and they call them not independent. So let's see what they are. There we go. It's that one. And anything else I've missed? I think I've done most of these. Oh. Okay, question 11 then. Suppose A and B are mutually exclusive, and the probability of A is a half and the probability of B is a fifth. Are A and B independent events? And explain how you know. Well, since these events are mutually exclusive, don't we know that the probability of A given B will be 0? We agree? When you're mutually exclusive, which does not equal the probability of A. And since they are not equal, they are, oh good, they're starting to use the word dependent. They are dependent. So if you know two things are mutually exclusive and you get some probabilities to go with it, can you see that you can then make the assumption about independence or dependence? Now, are A and B complementary events? That's a totally different thing. Are these two guys complementary events? Correct. Why are they not complementary? What should they add up to if they were?
1.
Would you agree they don't add up to 1? So we just have to go through this. We know that this is equal to, well, I know what it's equal to, so I'm going to have to find out. It's 7/10, right? So we know that there are 7/10. And since this is not equal to 1, they are not complementary events. And that's how that question would finish. Is there anything anybody has come to in the part B before we move on to the last section in probability? Was there any questions you want me to go over right now? In case I missed something. Okay, we still have tomorrow then. So we are now going to do the last bit of probability. It's going to take me a few minutes because I closed too many windows and I think I closed one I shouldn't have. There we go. And the last chapter is going to be evaluating probabilities. That's just its title. Okay. A few seconds to get myself sorted up. We should be ready. This is an example. There's only 5 questions, but they're long. And most of them, I think 4 out of the 5, use probability trees. Question 1 is going to be an example of that. So suppose that you are a magnet high school and you've got 11 and 12th graders. Make sure we've got that. You've got 11 and 12th grade students. And you're told that half are in each grade. So you tell me if I'm wrong, but if you're in the 11th grade, aren't you a junior? And if you're in the 12th grade, aren't you a senior? Would that seem reasonable? Okay, so let's keep going. So half are in each, right? And what else do you know? Half of the senior class and 50%. Oh, okay. Let me redo that because I misread it. Oh, I didn't misread it. Half are in each grade. That was correct. It's just the next one happens to have 50% in it. Now, if you look at just the seniors, half of them are in calculus classes. And if you look at the juniors, in the seniors, 40% are in calculus. Okay. God, I made that harder than it was. We are going to create a tree diagram, and then from that tree diagram, we're going to create a table with how many seniors and juniors and percentages and all that good stuff. So the first thing we're going to do is split them into junior and seniors. And since it's half of them, let's just stick to decimals. Would you agree that the split is 50% junior, 50% senior, right? That's the split. Now, if you're looking at the seniors, there is a calculus or not calculus, right? So they take calculus or have taken it, or they've not. And for the seniors, it's 50% are in calculus and 50% are not. And if you do the juniors, it's 40% are taking calculus, so calc. 40% are taking calculus, and then the ones that are not taking calculus is the other 60. Have you noticed when you do a tree diagram, if there's 2 branches, they always add up to 1, right? So if you tell me just one of them's 40, I know the other has to be 60. In this case, it kind of told us everything. This allows us to create a table, which I'm now going to do over here, where inside it, I'm going to put the probabilities of various combinations happening. So you could be a junior, or you could be a senior. You could be taking calculus, or you might not be taking calculus. Now, if you remember how the tree diagram works, right? If I follow this pathway, 0.5 times 0.4, can you trust me that you eventually get 0.2? And if I go 0.5 times 0.6, you eventually get 0.3. And if you go the senior route, 0.5 times 0.5 gets me 0.25, and senior, multiply them, and you get 0.25. Are you comfortable how I got the end destination probabilities? You just multiply the roads that took you there, right? So 0.5 times 0.4 get me 0.2. That means I can now fill in this table. This number here, this 0.2, is the probability that you're a junior who takes calculus. So a junior who takes calculus, its probability goes there. Now, a junior who doesn't take calculus goes here. A senior who takes calculus, and sorry, 0.25. And finally, a senior who does not take calculus is 0.25. Are you comfortable how these four guys are really these four guys? Now I'm going to find some totals. If you add everything up, what would you expect the total to be? If you add all four of these probabilities together, what would you expect? 1. And guess what? It is. If you add these together, you get 0.45. If you add these together, you get 0.55. If you go down this way, you get 0.5. If you go down this way, you get 0.5. So far, so good. Now, this table is a probability table. It contains probabilities of certain things happening. So if I looked at this table, I could say there's a 0.3% chance that if I pick a student from this school, they're a junior who doesn't take calculus. And this number here, if I pick a student at random from this school, the chances that that student is a senior and takes calculus is 0.25. So far, so good. Now, suppose we know one more thing. This school, which only has juniors or seniors, has 300 students in it. I should be able to create a frequency table. And the frequency table will tell me how many students are in each of these categories. So since I'm running short of room, junior, senior, calc, and not calc. Okay. 0.2 chance that you are a junior who takes calculus. If there's 300 students, wouldn't it be 0.2 of 300? 60 students. Do you see how I found that? The probability of it happening times how many people you were trying it on, right? 300 at that ratio. If you do 300 at this ratio, you get 90 students. If you do this one at this ratio, I guess my numbers might not be perfect, but that's not my fault. I'm only copying what I've got. You get 75, and you get 75. And this row adds up to 135, and this row adds up to 165, and the total adds up to 300, and this column adds up to 150, and this column adds up to 150. And whew, that table was what they were after in just question 1. So you can imagine why there's only 5 questions, because of the work you have to do. I had to rush it a little bit at the end. Are we okay as far as it goes? Tree diagram gets you a table of probabilities. Table of probabilities get you a frequency. If you really wanted to, couldn't you cut out the middleman and just take these numbers and get them? I just think the table helps see visually what's going on. Right, say hi, say your last name and bye-bye. And I'm going to be hanging about because I have some people who want to ask me questions. Lauren, you have a question, right?
Yes.
Okay, go for it.
Number 6 in part A.
Okay, number 6 and 7 part A. Gotcha. Let's
The,
go. Do you have it handy? Or
yes.
is it easy to write down? Do you want me to share screen or what?
I can write it down on my notepad.
Right, just tell me what you got.
Jill and Zoe have lunch together.
Oh, yes, I know it. Don't need to go any further. It's how to make it fit in the thing.
Yeah, I've tried it like 4 different ways, and I was
Right,
like,
let's tell you the last way to do it.
okay.
Yeah, yeah.
I've done
A
lowercase.
horrible question. Here we
capitalized.
go. It's Jill, comma, Zoe, with little brackets around it, comma, Zill, comma, that one, comma. You could have that one, comma, and you could have that one. Right, so you want to do that right now while we're waiting?
Yes. I didn't do the brackets, their own individual ones.
I didn't think they needed them either. I had to go and look at what they were looking for because unless the example they gave did those brackets, in which case that would be okay, but I couldn't see in the instructions either what they were looking for.
And group, comma, space. All right, now let's try it. Please be right this time.
I can fix it if it's not.
Still not right.
Okay, I'm going to go in and look at your specific one. That's the only way this is going to work. Okay, so we're in A. I'm going to look at scores. We're going to look at yours, Lauren. With a T in it. There we go. It's the only one you're having trouble with, right? Because you've done everything else.
Yes, it was the only one. I was like, why is it this? Like math, I'm getting down, like actual math. I was like, what is going on? Why is
I've
it
lost
open?
it. What? It's question 6.
Question 6, part A. And I was like, there's not extra ones because there's only.
Oh, you put an extra bracket around the whole thing.
I didn't.
You did. You did.
Oh, it
this.
added it. Hold on, let me add one more. Oh, stop. Add one more. Let's see if that. Where did it? Okay, it took it that time. It added a bracket when I was putting it in the brackets.
Well, I think when you click on it, it's trying to help, but it's hurting because it's put the start of the bracket to make you think, oh, you want a bracket? Okay, I'll do the rest with brackets. I think.
I got it right this time. I took out those brackets. Thank you so much. It was so frustrating.
I can imagine. Then that's you. Move on. Nothing to see here. Because you were doing it right. You just
Yeah, I know. I was like, there's not any more letters. What's going on? Ugh. Thank you so much. Enjoy your next
Not a problem.
class.
Right. See you tomorrow. Yeah. See you tomorrow.
Bye.
Bye. Hi, Deegan.
Hi.
Okay, where do you want to start?
Okay. So first thing, hold on, let me get my homework pulled up. Okay. So for Monday's homework for numbers 17 and 18, you had like gone over them and walked us through step by step. So I like followed along my numbers, and I'm pretty sure 17 we had the same numbers. And I walked it through out on paper. Like I have my work right here. Both answers I got, they were both wrong. Like
Okay,
when
what I'm going to do then is I'm going to go into WebAssign. I'm going to pull up your thing and we'll see what is on. What section was that in? 7A or 7B? Or what homework was that from?
It was A, so it was Monday's homework. So chapter 7, Introduction to Probability A.
I gotcha. Right. So you're in my 1 p.m. class, right?
Yes.
Okay, so I need to find you, Nyman in. Okay, and then go to scores. And it was A, so we should be able to just click on responses. And it was question 17, you said?
17 and 18. So the
17 and 18. So suppose the one, okay. Oh, I know what you've done. At least I know what you've done in 17. So let me put that one over here and I'll just go through it again and show you. You're well on your way to doing it right. Okay, so 17, keep going. So suppose the probability of winning a particular casino game, so the probability that you win is 0.4. So the probability that you lose is going to be 0.6, right? So that's fine.
Yep.
And they're independent. If someone plays the game 4 times, what's the probability of winning at least once, right? That's the guy we're after. Well, whenever you get one of these at least questions, it's better to do the opposite. And the opposite of winning at least once is that you lose all 4 times. And that fella you can get by multiplying 4 times, because you're losing 4 times in a row together. Yep. And so it's 1 takeaway, nothing 0.6 to the power of 4. And 1 takeaway 0.6 to the power of 4 gets you the 0.8704. What you did was you only found that guy, and that's the 0.1296. But if you take that guy and do 1 take him away, there's the right answer. So you were almost there. You just didn't take it away from 1.
Okay.
Okay. So you were on the right track for that one. Let's look at 18 then. And this is a restaurant story, right? And in this story, you get a big tip. So I'll call it B for big tip. And a big tip happens 20% of the time. So the chances you get a small tip must be the other 0.8. Right, so we'll start with that. And then in this story, it's 5 tables. And what's the probability that she sees at least 1 tip? So the probability that she gets at least 1, let's check this out, it's 1 big tip. It's going to be 1 take away the opposite of that. And getting at least 1 big tip is the same as getting all 5 being small tips. And so it's going to be 1 take away, nothing 0.8, nothing 0.8, nothing 0.8. So I'm just going to call that to the power of 5, because it is 0.8 times 0.8 times 3 times 4 times 5. And on our calculator, 1 take away 0.8 to the power of 5 comes out to be 0. Why is that? Oh, well, can I redo that? This number is 0.22 because I misread it, and that's 78. So there. Same process, slightly different numbers.
Mhm.
1 take away 0.78 to the power of 5, and that ends up being 0.7113. Oh, you did that one right, except you
I
didn't
missed my
round off. You
Well, also,
rounded.
I accidentally put 7 instead of 1.
Oh, I didn't see that part. Right.
Yeah. So
Yeah.
on my calculator, yeah, I got that same answer, but then on my paper, when I was working it out, I wrote down the wrong thing.
So the good news here, Tegan, is you're doing it right. You're doing it the right way. The first one, you just forgot to subtract it from 1, and the second, I guess you hit the wrong button when you were doing it on the calculator.
Yes. So I did 18 right, just accidentally wrote down the wrong answer on my paper.
Yeah, but you can fix that now, right? You can put in the right one.
Yeah.
Okay, what we got now?
The next one was number 13.
Is it same section?
Yes, same homework
Okay,
assignment.
I'm looking at it right now. So, that's that very long question, isn't it?
Yes, and
Okay.
that's why it was a little overwhelming, and I didn't really know where to start.
Okay, let's just start it with 13. Right, in an election, 62% of the voters were Republican, right? And so I'm going to do a tree diagram for this one.
Okay.
So you've got people who are Republican, and of the voters are Republican, and 38% was not. So I'll call them not Republican. And we're told that 62% were Republican, so 0.62 goes here, and 38% were not Republican, but I could have guessed that because don't they always add up to 1 anyway?
Mhm.
So they told me something I didn't need to know. Now, of those that were Republican, 70% voted for candidate X. So 70% voted for candidate X. Of course, how many people did not vote for candidate X? Well, it always adds up to 1, right? So if 0.7 do it, 0.3 won't do it.
Okay.
And then the people who are not Republicans, 5% of them voted for candidate X, and the rest didn't. Now, candidate X, 5% is 0.05. What's the not X going to be this time? Okay, so this is 0.05. What's the not X, this pathway here? Remember, they always add up to 1. So if you know 1, you can get the other.
5.
Correct. So that's the tree diagram constructed. Now that I've got that done, I can answer all sorts of questions that they're now about to throw at us. They're calling A if you vote Republican, and they're going to call B you voted for candidate X. Okay, so the first one was, what's the probability of A? So if you convert that into kind of words, what's the probability that you voted Republican? And that one was a baby one because it's really here. It's just 0.62.
Okay.
Then the next one is, what's the probability of a complement? Isn't a complement mean not voting Republican? Right. So if you want to say what's that, it's just stick the word not in front of it, and you very often get a good idea of what you're after. And the not Republican vote was the other 0.38. You see these numbers are coming from my tree diagram.
Yep.
Now, the next one are conditional probabilities. So the probability of, I've lost the damn thing, A, B given A, here we go. B given A is the probability that you voted for candidate X, given that you were a Republican. Now, if you tell me you're a Republican, which is this guy here, that's the people who voted for X, 0.7. So I got that number
Okay.
by saying, okay, I know you're a Republican, so what's the chance you were X? Now, the probability that you voted for X, given that guy. Well, that would be the probability that you voted for X, given that you were not a Republican. So I go here and I say, okay, if you're not a Republican, you're here. What's the chances that you voted for X? 0.05. Okay. Now, find the probability of A and B. So this is the probability of that you voted Republican and at the same time you voted for candidate X. That's what that and would look like, right? Voted Republican, voted X. Now on my diagram, when you find people who are Republican and voted X, you see it's this top pathway, right? You voted Republican and you voted X. And whenever you want to do a probability made up of from here to here and then from here to here, what you do with these two fellas is you multiply them together.
Okay.
So if you take 0.62 and you multiply it by 0.7, we get 0.434. Are you comfortable with that guy?
Yes.
Right. And then it says write in words. Well, that's pretty easy. And the answer is the probability of being a Republican and voting for X. There's choices there, but it's in my case, it's the fourth one. Now we have, I think it's called C, the probability of AC and B. I'm going to turn it into the probability. AC is not voting Republican, right? So you not voted Republican.
Okay.
And B is, oh, you voted for candidate X. I should just say voted X, right? Now, on my pathway, a not Republican who then went on to vote X is that pathway. And that ends up being 0.38 times 0.05. And that is, oh, this number here is 0.434. This guy is, let's do that, 0.38 times 0.05. And I come up with 0.019. Are you comfortable with that? Have you noticed that this tree diagram is basically the source of all answers? You just have to know how to read it, how to get the numbers you're looking for.
Yes.
Good. And then it says do it in words. Using the parts to B and C, find B. And what's B? Okay. So now we are being asked to find the probability of B. And that is the probability that you voted for candidate X. Well, I'm going to have to add some stuff here, but have you noticed that the people who voted for candidate X are these two ones here, right? Here and here.
Mm-hmm.
And don't we already know what each one of those is? So what do you think I'm going to do to get the total probability of people who voted X using these two fellas? What do you think I'm going to do?
0.7 times 0.05.
Oh, we don't need to multiply any of these numbers. So I'll try that again. There's a 0.434 who are Republican who voted X, and another 0.019 who are not Republicans who voted X. So how can we use these two numbers, which are basically these calculations here? How do we use these two answers to find the people who voted for X, regardless of party?
So from B and C then?
Say that again?
So from B and C, the two numbers that we got, would you add them?
Yes. So you would go 434 and you'd add 019 and 453, they tell me, which I'm not arguing with, it sounds right.
Okay.
And then the last one is a rather weird one. It says use the result from D, which is this one, right, to find out what percentage of them. So I was looking, I'm thinking, but I already know the answer. And then it dawned on me. That's the answer as a decimal. All they wanted me to do was to find out what it is as a percentage.
So you just move the.
Yeah, you multiply by 100, so you can move the decimal point 2 places.
Okay.
So the key to doing this was to realize that the tree diagram had everything you needed. You just needed to figure out where to get the information from.
Mm-hmm.
Yeah, we got anything else?
Yeah, one more thing.
Good. Well, not good that it's one more thing, but sure. What is it?
Just a second. Okay. Actually, I think I can probably do.
Which number is it?
Number 12.
Okay. Right. 12 doesn't need a tree diagram, right? You can do question 12 by just combining the probabilities in various ways. So let's look at it. I'll write it down, and you can just to check that you're good. So event A is first digit is odd. Okay. Event B is the first digit is even. And event C isn't even to do with that, it's to do with the second digit, and it's the second digit is odd. Okay. So let's start with the first one. What's the probability of getting A? So what's the probability that the first digit is odd? Well, there are 10 digits, right? The digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? There are 10 digits if you count them up.
Mm-hmm.
What's the probability that you randomly choose a digit then and it's an odd one, which is this question?
Would just be 1/2?
Yeah.
Okay.
And question B, what's this fella? Well, would you agree the chances getting an even digit are also a half?
Yes.
Right, so that one wasn't worth asking you, right? Because it's right. Okay, now this one is a trick question. And I'm going to put it in English. What's the probability that the first digit is odd and at the same time the first digit is even? It's a trick question. What's the problem? Yeah, because you can't have both, right? You can't be both at the same time. Question D. What's the probability of A or B? So what's the probability that the first digit is odd or it's even? That's a kind of interesting answer. It's not I don't think it's a trick question, but it's a very easy number. What's it? The first digit's odd or it's even?
Would it just be 1/2 again?
No, just one. Right. Half the time it's odd, the other half it's even. Essentially, if you add them together.
Okay.
I don't have room here. There, right? You get one.
Okay.
Now the next and is different. This is question E. And it's a probability of A and C. Now, A is the first digit being odd. And at the same time, the second digit is odd. Now that's not 0, because isn't the first digit totally different place than the second digit?
Mm-hmm.
And when you have two things and they are independent of each other, you can just multiply them together. So the chances that you get an odd one in the first digit is 1/2. The chances you get an odd one in the second digit is also 1/2. And so the chances of both those happening, that's what and is, both of them happening, is 1/4.
Okay.
Are you good with that one?
Yes.
Okay. Now, what's the probability of A or C? So it's a probability that the first digit is odd or the second digit is odd. That's a sneaky one.
I have no clue.
Yeah, it's hard to imagine what that would be. So what I'm going to do is I'm going to find a different probability. I'm going to find the complement of that, because I think that one I can calculate. So what's the exact opposite of the first one being odd or the second one being odd? Isn't that the same thing as both of them being even?
Mm-hmm.
Wouldn't that be so I can find the chances that both are even. The first one being even times the other one being even. So what I did is I changed the question into I don't know how to do it by finding its complement. And if you're saying, well, how do I know both are even? Isn't it the first one is even times the second one is even? And each of them are 1/2. So 1/2 times 1/2 is 1/4.